Go was designed with concurrency as a first-class feature, not an afterthought. Where other languages bolt threading on through libraries, Go has the Go keyword baked right into the syntax. One word launches a concurrent task. But the real story is deeper than a keyword. It's a model of computation called CSP that makes concurrent code composable and easier to reason about. This episode covers what concurrency actually is, why Go's approach is different, and how Goroutines work: creation, lifecycle, scheduling, and the patterns that keep concurrent programs from going wrong. These terms get used interchangeably, but they mean different things. Concurrency is about structure, designing a program to manage multiple things at once. Parallelism is about execution, actually doing multiple things at the same time on multiple CPU cores. The classic analogy: a restaurant. Concurrency is the restaurant's ability to take multiple orders, prepare multiple dishes, and serve multiple tables. That's the design. Parallelism is having multiple chefs working simultaneously. That's the execution. You can have concurrency without parallelism, a single CPU core switching rapidly between Goroutines. You can have parallelism without good concurrency design, multiple cores all working on one badly structured task. Go gives you both. You write concurrent code, and the runtime automatically leverages parallel hardware. Why does this matter? Sequential code for 3 1-second operations takes 3 seconds. Concurrent code for the same 3 operations takes 1 second. They all run at the same time and you wait for the slowest. This is the fundamental value proposition. Go's concurrency model is rooted in CSP, communicating sequential processes, a mathematical model from Tony Hoare in 1978. The key idea: independent sequential processes communicate by passing messages through channels, rather than sharing memory. The practical consequence is captured in this Go proverb: in most languages with threads, you share data by putting it in a shared variable and protecting access with a mutex lock. This works but creates problems. You can forget the lock, hold it too long, or acquire 2 locks in the wrong order and deadlock. Go's model inverts this. Instead of one piece of shared memory that multiple Goroutines touch, you pass ownership of data through a channel. Only one Goroutine has the data at a time. There's nothing to lock. 2 primitives implement this: Goroutines, the sequential processes, and channels, the communication conduits. We cover Goroutines today, channels in the next episode. Creating a Goroutine is a single keyword, Go. When the runtime sees Go, it 1. Creates a new Goroutine 2. Allocates a small initial stack, 2 KB, compared to OS threads at 1 to 2 megabytes, 3. Schedules the Goroutine for execution 4. Returns immediately. The calling code does not wait. That last point is critical. Go is non-blocking. Execution in the calling Goroutine continues the instant after. The launched Goroutine runs concurrently. Named function. Anonymous function. More common in practice, anonymous Goroutines are useful when the work is tightly coupled to the launch site, or when you need to capture variables from the surrounding scope. The main Goroutine problem. Every Go program starts with exactly one Goroutine, main. If main returns, the program exits, even if other Goroutines are still running. This code has a bug. You need to wait for Goroutines to finish. The standard tool is sync.waitGroup. WaitGroup has 3 methods: add n, increments a counter, done, decrements it, always use with defer, wait, blocks until it reaches 0. Start Goroutines in a loop. Note: pass I as argument ID, don't close over it. Before Go 1.22, all closures in a loop would capture the same variable, ending up printing the same value. In Go 1.22+, loop variables have per iteration semantics, but passing the value explicitly is still the clearest intent. Why are Goroutines called lightweight? 3 reasons: stack size, scheduling, and multiplexing. Stack size. OS threads start with a 1 to 2 megabyte stack. A Goroutine starts with about 2 kilobytes and grows dynamically as needed, up to a configurable maximum, default 1 gigabyte. This means you can create hundreds of thousands of Goroutines without exhausting memory. User space scheduling. OS threads are scheduled by the kernel. Context switching requires a privilege level transition, which is expensive. Goroutines are scheduled by Go's runtime entirely in user space, no kernel involvement. The scheduler decides when to switch goroutines and does so with much less overhead. N multiplexing. Go's scheduler uses three concepts: G, a goroutine M, an OS thread, machine, P. A logical processor M goroutines are multiplexed onto N OS threads, with N typically matching the number of CPU cores, controlled by GOMAX-PROCS. When a goroutine blocks on I/O or a channel, the scheduler detects this and runs another goroutine on the same OS thread. The blocked goroutine's OS thread is freed to do other work. This is why a Go server with thousands of concurrent connections only needs a handful of OS threads. Work stealing. Each P maintains a local run queue of goroutines. When a P's queue is empty, it can steal goroutines from other P's queues, keeping all CPU cores busy without manual load balancing. To demonstrate scale, this would be impractical with OS threads. A goroutine moves through 5 states. 1. Created, the Go statement executes. 2. Runnable, queued, waiting for CPU time. 3. Running, actively executing on AP4. Blocked, waiting on I/O, channel, mutex, sleep. 5. Done. Function return. The scheduler is preemptive in modern Go 1.14+. Even CPU-bound goroutines that never call any blocking function will be preempted at safe points, so they can't starve other goroutines. When does the scheduler switch? For triggers, a goroutine calls a blocking operation, channel, syscall, sleep, runtime. Ghost yields explicitly a new goroutine is created preemption. The goroutine has run long enough runtime. Ghost is rarely needed. Modern Go's preemptive scheduler handles CPU-bound work, but it exists for fine-grained cooperative control if you need it. You can also read the number of CPU cores and control GOMAX-PROCS. By default, GOMAXPROCS equals runtime.number CPU. Increasing it beyond the number of cores rarely helps and can increase scheduler overhead. A goroutine leak is a goroutine that never terminates. Since goroutines consume memory and a goroutine slot in the scheduler, leaks cause slow memory growth, the classic "my server leaks memory over time" bug. The most common cause: a goroutine blocked waiting for input that never comes. Fix: always give goroutines a way to exit, typically through a done channel or context. Context. The context package, covered in a later episode, provides the standard mechanism. Rule: every goroutine you launch should have a clear termination condition. You can monitor goroutines with runtime.number goroutine. In tests and production health checks, unexpectedly growing goroutine counts are a reliable leak signal. 5 rules for goroutine hygiene. 1. Always wait for goroutines to finish. Never let main or a parent goroutine return while child goroutines are still running. Use wait group or channel signals. 2. Pass loop variables as arguments. Don't close over loop variables in goroutine closures. Pass them as function arguments to be explicit about which value each goroutine gets. 3. Every goroutine needs an exit condition. A goroutine that can't exit is a leak. Design for cancellation from the start, not as an afterthought. 4. Don't launch unbounded goroutines per input item. If you process 1 million items by launching 1 million goroutines, you've traded I/O waiting for memory pressure and scheduler thrashing. Use a worker pool, a fixed number of goroutines reading from a shared work channel. 5. Handle errors from goroutines. Errors inside goroutines disappear if not explicitly communicated. Channel them out to the caller, or use airgroup, covered in a later episode. Concurrency is program structure. Parallelism is execution. Go handles parallelism automatically. You focus on structure. Go's model is CSP. Independent goroutines communicate through channels. Don't share memory. Communicate. GoF launches a goroutine. It's non-blocking. Main exits if you don't wait. Sync.waitGroup is the tool for waiting. Goroutines are cheap. 2 kilobytes initial stack, user space scheduling, n multiplexing. You can run hundreds of thousands. They can still leak. Give every goroutine a termination condition. Next episode, channels. The typed communication conduits that connect goroutines and make Go's concurrency model actually work in practice. This course is based on the complete guide to Go programming. Available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 14.